In this lesson, we're going to talk more about permutations. We're going to put it together with probability, and we're going to solve some problems. So, remember that the theoretical probability of an event A is given as probability of A, P of A, is equal to N of A over S of N of S. And so, N of A is just the number of ways of being successful, doing something successfully, whatever it is. And by successful, we mean whatever it is we're measuring. And N of S is just the total number of ways that something can happen. So let's just get to our first example. Software for generating multiple choice tests randomly assigns A, B, C, or D as the correct answer. On a 10-question test, what's the probability that all 10 questions have C as the correct answer? Okay, so let's let event C be that all 10 questions are C. In other words, I'm just choosing C as my event, and what we're going to see, we're going to measure the probability that all 10 of the questions end up having C as our correct answer. So, if we want to find the probability of C, then that's going to be P of C is equal to N of C over N of S. Okay? Well, what's N of C? N of C is the number of ways that we can do this. How many ways are there to come up with all 10 questions and have an answer of C? Well, there's only one way. Just if every single question has C as the answer, then that's it. Another way we could think about it, though, is for each question even, there's one way on question 1. I could lay out my 10 lines, so to speak. Actually, let's do that instead. I can actually show it. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, so question 1, how many ways can we have C as our answer? We've got 1, 2, 3, or we've got A, B, C, and D as the possible answers, but we only want C as our actual answer, so there's one way to do that. Same as there's only one way to do question 2, have C as be its answer. And there's only one way for C to be the answer of question 3. There's one way only for each and every one of these questions to have C as the answer. And using the fundamental counting principle, we do multiply these together. Can't seem to write a time sign here. There we go. 1 times 1 times 1 times 1 10 times can be thought of as 1 to the 10, and that is our N of C. So that just equals 1. So N of C equals 1. How many different options are there, though? Well, if we go back, and maybe I'll just use what I've already got highlighted up here, and I'll just repurpose it. On the first question, there's actually 4 different possible answers, A, B, C, or D. And there's 4 possible answers for question 2. And in fact, there's 4 possible answers for every single one of these questions. And these are all independent, so it doesn't matter what I had for one question. The next question still has those 4 options. So N of S turns out to be 4 to the exponent 10. 4 times itself 10 times. I'll just write that as an exponent. Otherwise, it's going to be a very big number. If we go to our calculator, 1 divided by 4 to the exponent 10 equals 0.0000009573, so 6 zeros after the decimal. $9,537. So that is a very small probability indeed. And if we want to make it into a percent, we could just move the decimal place 2 to the right and call that a percent. But whether we think of it as a decimal or as a percent, we can tell that it's extremely unlikely that all 10 questions are going to come up as C. But anyway, that's not the point. The point is that's how we can use permutations to help us figure this out. Well, not really permutations, I guess, in this case, because we didn't use our permutation symbol. But that is coming soon. Not to worry. The keypad for most secure entries to garage door openers use 4 digits out of 10 with no repetition. So no repetition, okay. What is the probability of guessing the correct code with no prior knowledge? All right, so let's say that event A is guessing the correct code. So there's only one correct code, isn't there? So n of A is going to equal 1. N of S is going to be all the different combinations that are possible. Well, if there's 4 spots, again, let's just draw the picture out. If there's 4 spots, then there's 10 possible numbers I can put in the first spot, but then after I've used one, I'm only allowed to use 9 for the next, one of the 9 for the next spot because there's no repetition. And then I can only use one of the 8 for the next spot and 7 for the final spot. So I could multiply that out, but that is also equal to well, if I want to put actual numbers in here, 10p4. So I've got starting at 10, and I'm arranging 4 of those numbers. So that's what n of s is. Let's just move this over here and call this n of s. So probability of event A happening is 1 over 10p4. Unfortunately, again, on my iPad calculator, I can't do permutations. So you could do this. You could do 10p4 on your calculator, but I'm going to have to resort to doing 10 times 9 times 8 times 7. .00019. Let's just round that to 0.0002. Which would be the same as 0.2%. Part B, guessing the correct code if you know what the 4 numbers are but not the order. Okay, if we know what the 4 numbers are, we no longer have 10 to guess from, do we? We have only 4. We know what the 4 numbers are, we just don't know what the order is. So in that case, we still got our 4 spots, but instead of having 10 choices, we just know that one of the 4 numbers goes in the first spot, one of the 3 remaining in the second, and then 2 and 1. So it becomes 4 times 3 times 2 times 1, which is the same as n factorial. Sorry, 4 factorial. But that's also the same as 4p4. Again, there's only one correct code, so n of A is still going to be just the 1. So the probability of guessing the correct code suddenly gets a lot better. Now it's 1 over 4 factorial. 4 factorial is just 24. I remember this one from before. 4 times 3 times 2 times 1. So I want 1 divided by 4 factorial. 1 divided by 4 factorial. There we go, nailed it. 0.042, let's say. Or as a percent. This one actually makes a bit more sense as a percent because it's closer to an actual number, and 4.2% would be the answer for this one. If you're dealt 3 cards from a standard deck, what's the probability that you're dealt a king, then 2 jacks in that order? Okay, so order matters. Order matters for permutations. Whenever it says that you're doing something in order, or even implying that we're doing something in a certain order, we definitely want to consider that we're using permutations. And of course, permutations is pretty much all we know right now, but in the next unit we're going to learn another technique called combinations, where order doesn't matter. Okay, so we're going to call this event A. Let's call it B. We just used A recently. So a king followed by 2 jacks is event B. All right, well, the number of ways we can do this. There's 4 kings in a deck. So standard deck means 52 cards. And out of those 52 cards, 4 of them are kings. So I've got 1 of 4 kings that I can choose. I could draw the slots over here like I'm used to doing, or I could just do it, over here by putting the numbers in. Let's do both at the same time. So I got 4 kings to choose from. So I got 4 in my first number. Then I've got 4 jacks to choose from as well. There's 4 of each kind of card. Once I've used a jack, however, there's only 3 left. So 4 times 3 is going to be my number for B. 4 times 4 is 16, and 16 times 3 is 48. So there's actually 48 ways that I could get this correct. So that sounds kind of promising. Let's see how many ways in general that we're able to pick 3 cards out of 52. Again, if I think about spots, I got 52 choices for the first card, 51 for the second, 50 for the last because I'm using up some of them. These are dependent events. That's the same as 52 P3, which unfortunately is actually a pretty big number. So the probability of event B happening, I know I'm all over the place here, my apologies, is 48 over 52 P3. And again, you can type 52 P3 in your calculator and see what you get. I don't have another calculator at my disposal right now, so I'm just going to do 48 divided by 52 times 51 times 50. And I got 0.0036199. Let's just round that to 0.0004. Which would be the same as 0.04%. So about 4/100ths of a percent. Pretty slim. And if that's not likely to happen, what's even less likely to happen is getting a specific king, such as a red king, followed by 2 black jacks. We'll make that be event C. So, N of C, I won't actually draw out the spaces like I did before, I'll just think it through. How many red kings are there? Well, there's 2 red kings. So I've got my choice of 1 of 2 red kings. And there's 2 black jacks as well. So I can have my choice of 1 of the 2 black jacks. But then I have to have another black jack, and there's only 1 left. So the 3 cards, I've got choices of 2 times 1. Turns out there's only 4 ways I'm going to be able to do this. My sample space doesn't change though. It's still 52. And I'm drawing 3 of them, so 52 P3. So P of C equals 4 over 52 P3. .00003, etc. I'll stop there. Or as a percent, 0.003%. So 3/1000ths of a percent, not likely. Recall the indirect method. That's where we subtract the number of unwanted outcomes from the total number of outcomes, It was given by this formula here. So the number of wanted outcomes is n of a. N of s is the total number of outcomes, and n of a prime is the unwanted outcomes. So we can do that. Sometimes it's easier to find the unwanted outcomes and approach it this way. Turns out we can do the same thing with probability. A total probability of something is 100% or 1. And if I just take away the probability, maybe it's easier to find the probability of something that I don't want, but then subtract it from 1 or 100%. And what's left is the probability of what I do want. It's because it comes down to this either-or dichotomy. Either I want it or I don't want it. And so if I know one of the two, then I can find the other. If there's a 30% chance of rain, but I want to know the chance of not rain, then 100% minus 30% means there's a 70% chance of not rain. As a decimal, that 30% would be 0.3, so in which case it would be 1 minus 0.3. So there would be a 0.3 probability of not rain. That's the idea behind it. What's the probability that in a room with 30 people, or a room with 30 people in it, has at least 2 people with the same birthday? At least 2 people with the same birthday. So that at least is something we have to constantly keep our eye out for. Because if something, when they say at least, it means there could be 2 people with the same birthday, there could be 3 people with the same birthday. There's nothing stopping us from continually, it could be all 30 people have the same birthday. Highly unlikely, of course, but not impossible. So I just want to point out that that's going to take an awful lot of work. So the number of the sample space, let's put it this way. Let's start with actually just a reminder. How many days in a year are there? 365 days in a year. So n of s would be, I'm not going to do it, but if I want to do spots like I've been doing here, I would have to draw 30 of these lines. And of course, these are independent events. Just because one person has a birthday doesn't mean another person couldn't have the birthday as well. So we can totally have repetition. So we got 30 spots here. I have 365 choices for the first person, 365 for the second, and so on. So I'm actually going to have 365 to the exponent 30 as my number of possible arrangements. Because once again, repetition is possible. If we say that we want, let's call event A being having the same birthday. As I already mentioned, it's going to be really hard to think of all the different combinations. So if I want to find the probability of at least or exactly 2 people having the same birthday, okay, that might not be too much work. But then I'd have to find out if maybe 3 people have the same birthday, or 2 people and another 2 people have the same birthday. So many different cases. Far easier in this case is to get the complement. So I want the probability of nobody having the same birthday. And in that case, that's not so hard to do. Because all we have to do, again, imagine I'm drawing 30 spots here. And, that's not 30, but the first person has a choice of 365 days for their birthday. The next person has 364. They could be on any day of the year except what the first person had. And the next person after that would be 363, and so on. This is definitely permutations. This would be n of a prime, in this case would equal the 365 days in a year, and we want to arrange 30 of them. That gets the repetition part out of the way. So the probability of nobody having the same birthday would be 365 p30 over n of s, which is 365 to the exponent 30. Okay, now I'm in a bit of a pickle because, again, I don't have a calculator to do permutations. I'm just going to take a double check here on this. No permutations on this calculator anywhere. So, I do have the number nearby, I think. Well, at least I know what the final answer is. I can't show typing this in because of my lack of calculator. I don't even have one that I can show on my camera here. But I do know what the answer should be from previously doing this. So you can confirm this. So on your calculator, do 365p30, divide it by 365 to the exponent 30, and what you should get, no I don't. I have a different number here. Oh my goodness. Calculator. Okay. I don't want to restart this lesson, so I'm going to make one little change. My apologies. Last time I did this, I did it with the number of people in the room, and there happened to be 29 people in the room. So in order to make this work without having to change the numbers, I'm going to fudge it. Let's make it a 29 person thing, and so that means I'll have to change this to 29, and I'll have to change this to 29, and then like I said, I've already got the numbers from the last time I did it in front of me here, so it'd be 365 p29, it'd be 365 to the exponent 29. Type that in your calculator. What you should get is 0.319. I'm sorry I can't do it with you. I know it works out. I've done this many times. I just don't have the actual calculator to show you right now. But assuming you type that in and you got 0.319, that means there's about a 32% chance of no one having the same birthday out of a room with 29 people in it. But if I want to find the probability that at least one person or two people have the same birthday, that's going to be the complement. So P of A is going to be 1 minus P of the complement of A. So 1 minus 0.319 equals 0.681, which is about 68%. Pretty high probability, it turns out. But again, the main point here is this idea of using the complement because it saves us. If we had to do this directly, it would be so much work, and using the complement makes it relatively easy.